38 on here. Okay, it's a big crowd. Okay, let's see. I'm seeing Johannes full screen here. I'm Bruce Kimball, and I've been trying to lead this group for the last, well, we've been going for a little over a year here on this round 2, but then there was round 1 before that. And so welcome to the AgMIP Maize ET simulation team here. And if I'm a little slow, it's because this is the time I usually get up in the morning. And so I had to rise early, but looking at what time the sun is up around the world, I realized that this time for me is probably the time when the most people all around the world are awake. So I hope that was true and that you can all partake here. Okay. I didn't send out a formal agenda of any sorts, but I thought that what we basically do is go around and do introductions to start with. And then I'd give a presentation of where we stand with round 2, a little review of a quick review of round 1, and then where we stand in round 2. When we get to that, I invite you to ask questions and discussion as we go along. And then towards the end, I wanted to bring up some preferences with regard to what statistics you like to use or would like to see me use for deciding the goodness of fit of all the models and ultimately what we should be putting in the paper. So with that, I'm going to just start going around the thing. Now I know everybody's got a different screen, so I'm going to go in the order in which I see people on my screen. So you're not going to know when you're going to get called, but that'll give you some idea of what I'm doing at least. Okay, Imal Wali, have to unmute yourself. Maria, can you unmute him, or does he have to do it himself?
Okay, I'm asking him to unmute.
Imal, I can see your mouth moving, but I can't hear you.
You gotta unmute yourself.
Can you hear me now?
I can hear you now.
Okay.
Tell us about yourself and what model you're working on.
I'm from Afghanistan. I work here with Sheikh Zayed University. My background is water resource management. I have been using metric models and some weather station data for the using Penman-Montet equations. So I'm not specifically familiar with the models. I just would like to know how, what simulation models are used for ET simulation.
Okay, thank you. I didn't recognize your name as being on the team, but I know that a lot of you have colleagues that are probably part of your team too. So anyway, thank you, Imal.
Thank you.
Okay. Paulino Ome. Can you unmute yourself?
Me?
Paulino, okay. I'm sorry if I'm pronouncing it wrong. Ome is the next person I see on my screen. Okay, let's move on then. Sebastian Gaylor. Hi, Sebastian.
Hello, can you hear me?
I can.
Yeah, I'm Sebastian Geiler from University of Hohenheim in Germany. My background is soil physics, and I'm running the AgMIP8 models, AgMIP8 Spaß and AgMIP8 G-Cross models.
Okay, thank you. Barsta Gold Zoltan. I see his number, his name usually is Zoltan, but I'm not sure how to pronounce Barksa. How do you say it?
Hi, can you hear me?
Yes.
Yeah, I'm Zoltan Bartsa, but I call it Bartsa.
But
Hungarian stuff. I'm from Hungary, from the Bushland University Department of Meteorology. Basically, my background is biogeochemical cycles, atmospheric greenhouse gases, but I eventually we are developing a model which is the so-called BioBGC MUSO biogeochemical model, also used as a crop model. And well, I'm a meteorologist, but focusing mostly on plant and carbon dioxide and evapotranspiration stuff.
okay, thank you. Next is Ken Booty. Ken is the person that twisted my arm and got me involved with this to start with. And as you know, I've been duplicating everything, sending it to him. So we have some backup here if something happens to me. So anyway, Ken.
Well, thank you, Bruce, for working with this. You're doing a nice job. I'm a DSAT crop modeler and have been working with the series Maize model. We have a lot of people, so we should go pretty fast with introductions if you can.
Right. Johannes Poelens.
Hi, Johannes, Aarhus University, postdoc of Jan Olesen, and I'm working with the DAISY model.
Garrett, good morning. Garrett Hogenboom.
Good morning, I'm Garrett Hogenboom, University of Florida. I work with DSAT crop models, in this case also with series Maize.
Jean-Louis Duran. Good morning, Luis. I can't hear you.
Sorry. Yes, is it better? Hello, Bruce and all. I'm Jean-Louis Durand. I'm the leader of the Maize group in AgMIP, and right now it's quiet because we're following up the crop water ET, which is led by Bruce here. And okay, so we're.
Might add that Jean-Louis has been leading the Maize team, and they did one study, and so a lot of you core people were starting from the Maize team and then got pulled into this ET one. Okay, thanks. Daniel, I can't see your last name up there. Good morning.
Good morning. I'm from Brazil.
I can't hear you.
Sorry, do you hear me? Can you hear
I
me?
think your volume is low because you look unmuted, but.
All right, my name is Daniel and I'm working with crop grow model from Dataset, and I have intention of use the Maize model too in the future. So I'm attending today for this meeting. Thank you.
Okay, thank you. I still couldn't hear you. I hope most of you could, and that made me realize that my microphone wasn't very close, so I don't know if you can hear me better or if that made any difference. Okay, Gene T. Nobody there, I guess. Good morning, Kelly Thorpe. Sorry to get you up so early. Kelly, you there? There he is. Hi.
Good morning. Yeah, it's quite early here, so forgive me. I'm still eating my breakfast and waking up. So yeah, I'm Kelly Thorpe, and I work with the DSAT team, mainly making the final runs and putting together the spreadsheets for Bruce. And we have, what is it, 18 or 20 versions of series and AgMIP Maize, so it's quite a task to put together all the data. But that's my contribution here.
Thank you. Kelly is at the same lab I'm associated with. Let's see, my screen just flipped around. Oh, here's another name, and I'm going to mispronounce it, but please introduce yourself. Dijbril Beg Ayoko. Okay, no response there. Let's go to Antonio Trabucco.
Trabucco, yes. Hello, everybody. I am from the Euro-Mediterranean Center on Climate Change and focusing mostly on interaction between vegetation, plant, and climate. We work together with my colleagues on the CMETO model. Thanks a lot anyway. Thanks a lot for this effort.
Okay, thank you. Yuyayo Zhu.
Hello, can you hear me?
Yes, I can. You're a little bit faint, but I can hear you.
Hi, hello everyone. I'm Hui Yang. My background in climate science and crop science, and I come from the Greenwich University. And I'm currently using the JUICE crop model, which is a UK Met Office. I also use the general large area model for crops from the University of Leeds. That's me. Yeah, thank you.
Yeah, okay, it was a different name there. Okay. Yuzu, is that?
So it's not me, right?
It's not you, yeah.
Okay, maybe it's me. It's me.
Yes.
Sorry.
Yes. My name is Yuyao Zhu. Yes, I'm from Beijing Normal University, and I focus on the desert models, and I'm interested in the extreme climate change to the maize. Yes, that's me. Thanks.
Okay. Okay, thank you.
Bruce, can I jump in here a second? You're going to run out of time because you've got about 50 people.
Yeah, I noticed that. So we got quite a few more people here than...
Your session's open, and I'm thinking you should go ahead and present your results.
Okay.
Sorry.
Well, with that in mind, I'll go ahead with that, and maybe we can finish up later on with that. Okay. So now at this point, I need to share my screen, and let's see if I can do that. Oops, let's see. Okay. So this is the title of the talk then that I have given. Okay, you can see this one says Agronomy Virtual Annual Meetings. Oh dear. Okay. I hope because I made one for you guys that's got more slides on it. And I'm not sure why I'm seeing that one. I may have goofed up. Okay, let's go with this one as best we can. And I may, in the middle of a meeting, have to jump over to another computer here. Okay. Share screen, here we go. So I'm back to this one. Sorry folks for that glitch. So anyway.
Well, Bruce, if you also find it later, maybe you could share it in email. If you find the other PowerPoint later, you could always share it.
Right. Well, it's got more slides on it than that I wanted to discuss this morning. That's the big problem. But anyway, as many of you know whose name appear here, as well as a few others, we started off doing a first round of this intercomparison. At that time, there were 29 different models, and we were using a data set that came from Ames, Iowa. And this is briefly is the conclusions that came out of that very first paper. If we looked at the mid-season ET rates, when we started off in what was a typical year, whether there's a huge spread among the models, a whole factor of 4 in what they were predicting for ET. And then after we moved along past the blind stage and gave all the available data to the modelers, why still the values are varying about a factor of 2. And they didn't improve very much in this first portion when most of the ET was just the E coming from the soil, but they did better in improving the T stage, so that was it. We noticed that a lot of the variability among the models was coming to what approaches they were using to calculate the potential evapotranspiration. And jumping ahead a little bit, I had you all provide more information about the steps that go into calculating this, but I haven't had time to look at that yet. But anyway, that will be one focus here that we're doing on this second round. The median of all the models was generally, but not always, a good predictor of what the ET rates were and some of the other valuables. Some models were better than the median, especially with regard to grain yields over the 8 years that we had data for from there. The best model predicting yield was not among the best half a dozen for predicting seasonal evapotranspiration. Some of the more interesting things that we learned came about because there were different flavors of the same models, and so we could just change one thing at a time. Now, with regard to the Dataset model, we found that an older Ritchie model for predicting soil evaporation performed better than what was now the default routine that's in there. And the Expert N model, there were 2 flavors of it. One was a simpler version, but it had a realistic root distribution, and that was able to do better than another version that had a detailed energy balance, but the root was uniform over the whole rooting zone. So anyway, those are a couple of things that came out of that first round. One of the things that surprised me, at least with this first data set, was that there were really a lot of different approaches, and particularly with regard to complexity. There are some really simple models and some really complex models, and yet they were comparable in their accuracy. One of the things I did notice was that the models that are widely used, and they were among the more successful. And that suggested to me, at least, that a larger number of users spread all over around the world over a lot larger range of conditions and time, and they've led to improvement of and a lot more testing. So with that, one of the problems, however, we had in that first round was that Ames data set. We discovered after we were into it that it must have a water table down there, and there weren't any deep soil moisture measurements to confirm that. But anyway, that involved a big complication. So that led us to where we are now, using these data sets from Meade, Nebraska, and Bushland, Texas. And I think we've got a couple good data sets here. Sorry to repeat this for those that are completely involved with this, but this is for those people that are just hanging on here and listening in to try to learn what all we're doing. Anyway, we've got a total of 6 rain-fed years from Meade, Nebraska, and 6 were irrigated. And they're using eddy covariance to get the ET rates. In Bushland, Texas, they've got Texas-sized lysimeters that are 4 meters on a side. We have 2 years of data with Maize, and they are using drip irrigation on half of their fields, half of their lysimeters, and those drip irrigation ones were all fully irrigated. And then they're also doing sprinkler irrigation. So we got 2 treatments years with full irrigation and 75% irrigation under the sprinklers. So that's the data sets we're using. They did a lot of measurements. So we've got, and I haven't analyzed any of this growth data yet, but we've got lots of backup growth data and soil moisture. The protocol that's being used is that we started off with a blind phase where you modelers were furnished the weather, management, soils, and initial conditions. And you all got your results back to me by the end of February for that. And I'll jump ahead a little bit more. And well, no, okay, that's right. Anyway, then we started phase 2, where I sent out additionally leaf area index, biomass yields for just the fully irrigated treatments. And you all got your results back to me by the end of September. But it was during the course of phase 2 that we realized that I had made a mistake in what the plant population was in some of the for the treatments in Meade for the fully irrigated case. So that complicated things and some delays. So we're not going to have the full 20 treatment years here. We're just going to have, what is it, 12? Yeah, it's 14 back here claims. In the data I'm going to be presenting to you, I've focused on what we got here with phase 2, where we had the correct plant populations, and I'll go back and try to analyze these more fully later. Okay, we're now in phase number 3. Just recently, I provided you with the evapotranspiration and soil moisture data for the fully irrigated treatments. And the deadline for getting those back is in the middle of December. I really urge you all to do it, please, before all the Christmas holidays come in, although this year may mean we're all staying at home and not traveling as much as we normally would, but in any event, let's move on and get phase 3 done. After phase 3 is done, we'll move on to phase 4, where I provide you all the data for all the treatments, and hopefully we can get that done during the first months of next year. As we go along here, if you've got any questions, why jump in and ask them, please. Now, this is the list of all the models that are participating in this, and you can see that we've got, you know, really quite a few here, and in some cases there's more than one flavor of them. in the case of the Dataset series Maize and AgMIP models, there are several flavors. And if we go to this next slide, I'm really impressed with how organized the Dataset group got together. And they are got all these different tests that are going on amongst different routines that are within the Dataset umbrella in order to run these models. We're redoing the test from between that early Ritchie method for getting soil E and this more recent one with Suleiman and Ritchie in it that is now the default in there. And Kelly Thorpe is really doing a lot of this because he's grabbed data on what the alfalfa reference would be for the potential evapotranspiration. And then it's coming also from the grass reference, which is the more common one, 12 centimeter grass, 50 centimeter alfalfa. And then the probably the most commonly used one is the FA056 method that uses the Penman-Monteith. And then the default method for getting the potential in the thing is this Priestley-Taylor one. And with these two, they're also running this hydrous soil water balance, which uses the, what is it, Richard's equation for moving the water around. And so that is a more sophisticated method than just the tipping water bucket method for moving soil water around. So we've got a total of 10 different flavors of series Maize within Dataset. And then also within the Dataset umbrella is the AgMIP model that John Lazazo from Spain has developed. And the same flavors are being run with it, except that they're not doing hydrous with it. So there are a total of 18 different flavors of these two. So a lot of tests, micro tests going on besides, so routines are getting tested besides just the models. The Nebraska data from Mead are coming from this field called NE2 right here. It's got a center pivot irrigation system. This particular photo shows another field nearby, which is in continuous corn or maize. We're not using that one. The rain-fed field doesn't have the center pivot irrigation system, and it's nearby. It's not within the field of view here. And I don't have a picture of it. I visited the site in August of 2019. This is a field I took in NE1, but it shows the kind of flux tower that they have out there. And this is what they call the radiation tower with the radiation instruments on it. It's painted black, so it reduces reflections. But anyway, it's the same kind of setup in NE2 and NE3, but my best picture, I thought, was this one. So, but anyway, you can get a pretty good idea of what their instrumentation looks like. And I don't have a good picture from the Lysimeters at Bushland, but this is what their field looks like. And this is where all of the micromet measurements are being made. And they have a linear move, they call it MESA, mid-elevation sprinkler application, I guess it stands for. Anyway, these are the heads of the sprinklers down here, and it'll come across. And they did 75% irrigation as well as 100% irrigation with that irrigation system. The lysimeter is down under here somewhere. Obviously, this isn't maize, but you get the idea. Okay, let's move on to some data. This is mead, which was irrigated. This is phase 2 data. And you can see that, I hope you're all familiar with box plots, wherein the green box shows 25% to 75% of where the model's values were. The whiskers go from 5% to 95%, and then the dots are the outliers from that. So you can see that with this irrigated field, that there's a lot of variation amongst the models from, so, and this is what we saw in the round number 1 with the Ames data. This is looking like there's still a very wide spread if you look at outliers that are below to the outliers that are way above. However, looking more closely as I compare this slide with what we had from the Ames data, it's encouraging in that the length of the green box is shorter than it was before. So a lot of the models appear to be doing better with these data sets than the before. Now, so that's the green box. Now the observed data are in orange, and the median is in blue, and of all the median of all the models. And as we go along here, we can see that the observed and the mean and median are actually doing pretty well in agreement for much of the year. Amazing that follow these big change from one day to another in this case. And that was true throughout all the year until the very end. And towards the end, when the models thought the crop was continuing to grow, but in fact, the real data show that it is pretty well shut down. Now, that was one problem with the data set, is it was really pretty hard to tell exactly when physiological maturity occurred, so that may have something to do with this. But in any event, even though there's a wide spread amongst the outliers, why in general, why models seem to be doing better. Now, if we move to the rain-fed field, it's kind of the same story, pretty good agreement up until we get into this period right through here, where the real plants were continuing to transpire, whereas your simulated ones in general were dropping off. So let's hope that doesn't indicate anything too bad going wrong. And then at the end of the year, again, the real plants were shutting down while the simulated ones are still going. So has anybody got any questions about these before we move on? This is just one example now, 2003, which happened to be the driest year, by the way, at Mead. Now then, let's move on to some data from Texas. These are, this one is the fully irrigated Southwest one. This was in 2013 data. So this is well watered. And as we go along here, you can see that on days when the the evapotranspiration was really high, I presume it was pretty windy or something like that, the simulated plants are falling below what was actually measured. And that was pretty consistent through the year. And towards the end of the season, why the real plants are shutting down, but the simulated ones tend to be continuing to go on. And also in Texas, it was hard to tell exactly when physiological maturity occurred. If we moved, whoops, sorry about that. If we move to the plot that's got 75% of the calculated water requirement, we can see that if you compare here to here, the actual agreement is better under the water stress conditions than it was under the well-watered conditions. And so anyway, that's kind of interesting that so when there wasn't any water stress, why the models tended to be missing the really high ET rates, but when there's a bit of water stress going on, they're actually doing better. Well, back here, when there was a lot of soil E going on, why again, they were missing it at this point, but when we got to mid-season, why it was being captured. Again, towards the end of the season, the real plants are shutting down and the simulated ones seem to be continuing to transpire, or maybe soil evaporation going on there too. Any more questions? Okay, this is just I grabbed a range of what I was seeing on the reports that are coming back. And you can see this is just 6 out of the 42 models. I certainly didn't think we had time to show this today, but you can see that model 47 did just a beautiful job here. Model 48, not so well. And this is kind of typically what I was seeing out there and all the rest of them. That's just to give you a flavor of what I was seeing on daily ET from the main Mead rain-fed field. Now, this is the root mean square error. Actually, it's the relative or normalized root mean square error of the simulated daily ET rates for all 42 models. This is for the 75% irrigation, 100% up here, and 75% irrigation down here. And this is the daily ET then. When did I tell you? Okay. So you can get some idea of how good or how bad the agreement is. Now with this normalized root mean square, you can see that the scatter then in the data is on the range then of 3/10 or so of what the observed mean data was. Now if you look over here on the right, there's what the median was. And you can see that a few of the models are really pretty close, and some in here, and then some are really, you know, having twice as much ET going on as what the median was. So you get some indication of how well they're doing. Now, if we look over here at the 75% irrigation one, why, it's kind of the same story pretty much. There's what the median was. Oh, by the way, you modelers know what your model number was, so you can pick this out. And for those people that are just visiting for the day, I numbered the models from 41 up through 82. And the reason I did that was I wanted model numbers that wouldn't get confused with the first round. So that's why these model numbers are what they are. Any question?
Bruce, I'm confused about a median.
Yeah.
Is that the median of all the models, or is
that's the median of all the models?
Because it seems to be less than any of the errors you show for the individual models.
It is lower. We want small values are good here. We want the lowest root mean square.
Bruce, am I correct in interpreting this not as the median of the root mean squared errors, but if you take the median of all models and then calculate the root mean squared?
Yes. Take the median of all the models. How well did it compare to the observed for all the daily ET? Okay. So here are just 6 out of the 42 graphs for observed versus simulated. This is the cumulative ET from -10 to 20 days after planting. So generally our experimentalists got out there and got rid of the weeds and got the fields ready before planting, and then for 20 days after, it took a week or so to germinate. So this is mostly soil dominant, soil E dominant ET that's going on here for all 20 of the treatments. So again, this is just the flavor of what I was seeing out there in terms of what got returned. Now, like, here's a model that was quite a bit underestimating what the observed was. Here, certainly got the slope right, but it was biased toward underrepresenting. And then this one over here is the median, and you can see there's a really, pretty good fit there, doing well. So that just is give you some indication again of what I was seeing then for soil evaporation. Now then, if we move on to +41 to +100 days after planting, this is where it would be mostly transpiration. And this is again for all 20 treatments. And I just again grabbed, well, 5 kind of random ones. No, they weren't random. I just wanted to show you a range of what I was seeing. And there's the median. Again, doing a pretty good job. The slope isn't quite there. Here's one, it's doing quite well. And here's another where it's very consistent in terms of being close to a regression line, but the slope of the regression line is quite a bit off. Here's one that looks like it was doing a pretty good job, but really missed it on 2 of the treatment years. Okay, this is the relative or normalized root mean square error of cumulative ET for, this is mostly transpiration up here, mostly soil evaporation down here. And again, here's the median off to the right. You can see that quite a few of the models are falling very close to the median across here, and then some are fairly far off. And then if you look at the relative, this is the relative error, in other words, but anyway, so comparatively to the total observed ET, are doing a much poorer job at getting E than they are at getting T. But if you stop and think about this, this is a 1-month period of soil E. This is a 2-month period of T. And so if you look at the observed amount of water that was lost during this period, why there's 4 times as much water being lost up here as there is down here. So overall, it means seasonally, even though they're doing a much poorer job at getting E, overall, for the whole season, because they're getting T right, why they're getting closer to what the total water use is. So any questions on this one?
Yeah, Bruce, I was wondering if this is Dennis Timlin.
Yes, hi.
I was wondering, these are fields are all no-till, right?
They are conservation till. That means that there's a little bit of tillage, as I understand it, a little bit of tillage going on just right where the row is, but that's all.
So there's some residue on the surface at the beginning of the season.
Yes, yes,
yeah.
yes. I tried to estimate that, but I've forgotten what I put down and what I sent you. Okay.
I had one other question too. Now, in your observations, were there a difference between the models that did hourly versus daily data in terms of how well they did?
I haven't looked at that. I'd have to go through and I didn't. You remember what your model numbers were? I think one is 80 and
73 was the other.
What?
73.
So you can, maybe you didn't want to.
Yeah, that's okay. No, we know there's a lot of work done on that part of it.
Yeah.
But it definitely the soil part for our model was not as good as the other part.
Right.
But the hourly, I think, was our daily. We have a daily version. The daily version was I think there's quite a bit of difference between the two.
Oh, which is in contrast to what you found in round 1. Well, anyway, that'll be an interesting side thing. Yeah, there are 2 flavors of Dennis's model. One is hourly, and they both do. I should let you tell us, but I'm talking. So anyway, they both do a full-blown energy balance, but one is using the hourly data as input, and the other one is using daily data that come from a simulated hourly curve. That's the difference, right, Dennis?
Yeah, but the real difference, I think the real effect is what happens with relative humidity. And it's quite different than how it's calculated on a daily basis and on the hourly one. And the model is very sensitive to that.
Ah, okay. So these are the conclusions from round 2 that I've got so far. And anyway, we can see that quite a few of the models are doing really quite a respectable job of simulating ET. And yet you can see from the scatter in the daily curve that I showed you that others are performing rather poorly. The median, again, has always been generally, but not always, especially at the end of the season, a good predictor of what was going on. Got a lot of analyses yet to be done, and because of the mix-up or the mistake I made in what I gave you for the plant population for the irrigated ones and thing, I've got to go back and redo a lot of work I already did for phase number 1, but since the heat was on to get these presentations done, I just focused on round 2 for this. So that's basically the talk then that I'm going to be giving at the agronomy meetings. Only of course I'll be going a lot faster for that. And so with that, well, I'll open it up for questions. I'd like to do a little discussion with, as I mentioned at the beginning, of again, what parameters you'd like to see me doing for evaluating how well the what to use for goodness of fit of the models. And with that, I'll throw it open for discussion here. We've got plenty of time. No questions from all of that? How many of you are mad at me for that plant population mistake?
Bruce, this is Dennis again. I'm not mad at you about that. It was good. Give me a chance to rerun the model. There's the other thing is, you know, how we discussed this before, and Sue and I were thinking about this, is the number of parameters in the models and what's the best way to address that. And some models can work well because they fit 7 or 8 parameters, and others might only fit 1 or 2 parameters.
Couldn't quite understand. You repeat it, please.
So you have I'll put on my camera here. You have with the models have parameters that they calibrate, or they have to fit to get the thing to fit the data. And so some models have more parameters than others. And so how do we is there a way to penalize a model that has a lot of parameters in a way that have to be fit?
Okay. Why don't you go ahead and answer the question, because you have sent me some material about it that I was expecting to address at some point, but I haven't.
I guess I have to think about it more. I'm not 100% sure. I know that when Sue and I discussed it, there's goodness of fit measures that can be penalized for numbers of parameters. And I guess it would depend how we fit the observed versus, you know, to get the statistics out of it. And I definitely have to be thinking about that a little bit.
Well, the other thing that comes in is that it depends a lot on the data set or sets that are being used, because I can easily envision that some of the simpler models can handle data sets that are close to what's typical, whereas the ones with more parameters can handle the extremes better. Does that sound plausible? By the way, that's pretty handsome beard you got growing there. That's the last time I saw you.
It's part of one here. They can't tell anymore because everything's white.
Well, I'm going the other direction in case you haven't noticed.
Bruce, I follow up. This is Ken Booty. I'll follow up a bit with what Dennis is saying. I've seen some of the other teams try to argue that, I'm not sure it works with the normalized root mean square, but there are ways to determine statistical fit relative to number of parameters here. But that's complicated. And at least looking at phase 1 or phase 2, there's not a lot of parameter adjustment that relate to soil water because everything's blind. I think what you'll find, particularly as you get into phase 3 and 4, which we're not finished with, is that soil water and how the models handle the degree of access of roots to soil water is going to make a difference. May not be water table, but it's still going to be some of the same problem.
Is that something that's a parameter that people most likely fit when they start getting more of the yield values?
Well, it's not so much the yield as this is what's great about this data set. Soil water measurements will be coming along later. And you'll know exactly whether you have your rooting placed well and your water uptake functioning well. So that's going to be probably one of the first teams of any of the AgMIP crops to look truly at soil water against measurements. And I think that's been this kind of blind thing that's happened in the past. It will be a nice thing.
Especially looking at different parts of the horizon where the water's coming from.
Yes.
Let's see. I got a request from Max for sending out to all of you the where we are so far on the results, and I guess I can go ahead and do that. I'll send you statistics and those, like I grabbed 5 random, not random, but a range of plots of the ET versus simulated ET versus observed. I can get that out to all of you so you can get some idea of how well you're doing so far. It sounds like does everybody want that? I'm going to jump over my other computer here. Oh. Kelly Thorpe has sent a couple photos of the Bushland lysimeters. Can you throw them up on your screen, Kelly? You probably do it quicker than I can since you had to pull them up.
Yeah, give me a minute, Bruce, to do that. Okay, Bruce, I shared a picture of the Bushland lysimeters.
Oh, excellent. Okay, so covering 4 rows of cotton here. So, and
yeah, I've been here. Basically, you can climb the little hatch that's in front there. There's a ladder, and you can climb down into them, and you go down maybe, I don't know, 15 or 20 feet or so and into the ground, and then you can see the outline of the lysimeter, which is the black there. And you can, once you go down into the hatch, you can see the scale and the bucket and everything. So it's quite impressive piece of technology.
oh, I thought it was on 4 load cells, but it's just one scale, huh?
Yeah, you may be right about the detail, but once you get down there, you can see the box and how they're doing all the weighing and stuff.
Okay, Maria, I'm going to be joining from another computer here.
Okay, that should work.
Okay, Kelly. Oops. Okay. So I'm leaving my other computer.
Bruce, you have to unmute.
Kelly, do you have another photo to show?
This one I have up shows it the best.
Okay.
Is that enough then? Or?
Yeah, that's great. We'll start using that one instead of the one I've got. But looking back, the one I've got, it's almost exactly the same, except the cotton has grown up much more. Oh, Steve, are you on the call here? Steve Ebbett? Never mind. Okay. Anyway, I'd like to see if he's got one with maize growing instead of the cotton. Okay, could you unshare, please, Kelly? Okay, I'm going to try to show the one that I prepared for this one. Yeah, AgMIP, great. Oh, I see what I need to do. Okay, well, this isn't ideal, but I guess we'll go with it for now because it's not switching over to full screen. Ah,
If you go into the tab called slideshow at the top,
yeah.
There you go. That works.
And where? I don't see, oh, end slideshow, you mean. What's happened, trouble is that I've got two displays going. And so what I want to show you is on my other display. So let's go back to where we were before. This will work. This is one slide that I just did last night that didn't make it into the agronomy one. And what it shows are the box plots for all 20 treatments, where this is each of the 20 different treatments, and then the box plots then are the range. Well, like I said before, the 25 to 75, so forth. And I think that this slide is really quite encouraging because this is the cumulative ET from the 2-month period between 40 days to 100 days after planting. And if you go along here, you can see that most of the models are coming really pretty damn close to what was observed for the mead data, whether it was the rain-fed cases or the one. Now, if we get over to the Texas cases, why, you can see that it's really not, they're really not doing too bad a job here either. The observed are higher than was getting, the models were predicting. And then this one is in the middle. But anyway, over this 100-day or 60-day period, why the models are, for many of them, are doing really quite a respectable job. So that's encouraging. Even if the daily AT wasn't right, why the errors from one day were getting canceled out in the next, apparently. And so the cumulative was doing quite a good job. Oh dear, this is sensitive. Now, if we go back and look at the period when around planting, when it was mostly soil evaporation going on, again, it's really pretty encouraging in that the observed and the medians here are pretty close. Here, on the rain-fed one, why the models are predicting more than what was actually observed. Now we get over to Texas, why again, this 1 year, and this is the example I was showing you as it turned out, was where the observed were higher, but then I look over here and onto the subsurface drip ones, when I look at that more closely, I can see that the observed and the models are actually doing a bit more than were observed there. So I think the cumulative story here is really pretty encouraging. Any questions on this one? Okay.
Yeah, just to talk. Hello, thanks, Bruce. I'm surprised, but maybe this is normal to see so much variability in the results from the drip irrigation, as well as 75 or 100% distribution uniformity.
I'm having, can you get your mouth closer to the microphone or something? I can't quite hear you.
My daughter is sleeping. No, nothing. I see the drip irrigation as well, the 75 or 100% is the one simulation with the larger variability in the results.
Yes, this one?
Yeah, I see this larger variability, exactly. So I'm really wondering if there is something that here we should consider in improvement of models, because it's maybe something in the distribution uniformity that we should characterize better, or I don't know if there are other characteristics, but I really think these are important aspects for irrigation modeling to consider.
I think so too. And then if you come back, here's the other 75% one. It's a much smaller band, but again, most of the models are getting below what the observed was. Here, their subsurface drip is, they're missing it here, hitting it right on here, so kind of surprising. But all in all, after looking at the daily data, this is really encouraging. Okay, here's some questions then that I wanted to ask you what you would like to see. This is model number again, showing how well your models were fitting the data. This is the period where it was mostly transpiration in the upper graph, and the bottom one is mostly the E part at the beginning of the season. Median's off to the right again. So if we just look at the correlation, this is what shows up. You want this to be up to a value of 1. You can see some models are falling pretty low here, but a lot of them are really close to that. Here's what the D statistic is. This is a favorite of Ken Booty, I know. Then you get some of these where it actually can go negative. There's a little bigger spread. Here's just the root mean square error. and get a lot bigger range here. The one disadvantage here is that this can vary all over the place, depending on just what the range of whatever you're looking at is. In other words, there's no 0 to 1 thing or anything like that going on.
Bruce, is this on the cumulative or is it on the day? Because you can do the same kind of statistics on the daily values too, at least the correlation.
I haven't.
And it has a different
didn't get around to that. I just did this one yesterday.
Yeah, it has a different meaning because if you do the daily values, then you're asking whether you pick up the high lows caused by, say, relative humidity, radiation, etc. Whereas
high
the
wind days,
that you're correct in the overall accumulation rate.
Here's what the normalized root mean square is. I kind of like this one because I have a feeling it's like a coefficient of variation in the sense that you get some idea how big the variation is compared to what the overall mean is.
I think I agree with you, Bruce.
Okay. Now here's what we did most of the work with in the first paper, where we calculated the mean square error and then partitioned it into this standard bias, non-unity of slope, and lack of correlation. So you can get some idea of where the most variability is coming from. Like the tallest peaks here generally are off on their bias. Like here's one where the slope was really pretty good, but the bias is same here. And then if you look along here, like on the median, the lack of correlation is generally, a lot of that is just the spread in the observed data. So that gives you some feel for that. So again, I think this is kind of a good way, but the problem with it is that you're going with the square, and so you get values that are really don't mean very much. So any comments on what you folks would like to see? And when the time comes to paper, I'm probably just going to have to go with one of these again, just because of the length of the paper. Maybe there'll be more than one paper, who knows, at this point. Oh, I thought there'd be some champions speaking up. Nobody out there with a favorite that they want to defend?
This one has merit, but it's complicated.
Right, right.
That's why the normalized root mean square is probably best.
You folks really like that one? I do anyway. But I like this, like that one too, but it is a lot more complicated and you don't get a good feeling for how big is big.
But it's very informative. From the modeling consideration, it's very informative. Also for internal use, I like it.
I couldn't hear you. Do like it?
Yeah, I think it's very informative to pitch
okay.
Modeling development. It's for internal use, for instance, I think it would be really nice.
Any other issues that people want to bring up at all? How are you coming along with phase 3? No progress yet? Well, if that's it, that's it. So I
Bruce,
guess
excuse
we
me.
can.
This is Dennis again. I'll bring up one more question. I think something to think about. And thinking about how the results are with the soil evaporation right from the beginning, before the crop, before the canopy has been fully developed. I mean, I think there's a lot of variation in how we simulate those things. Some of the models just do they sort of they subtract until you get to an air dry value, right? And then they stop. And others might use more of a hydraulic kind of component to it. And is there something in this analysis that can show us how we can improve that? It's maybe for everyone to think about what needs to be improved in that method. Is it really, does a more mechanistic approach really help? Or is there some way we can modify the approach of sort of like a capacitance-based model where you get to an air dry and then you just stop taking water out like that?
I think that what the DISAD group is doing, where they're comparing the Ritchie and the Suleiman and the Hydrus model, should shed some light on that. Certainly the Hydrus model, moving stuff around with the water potential and might help.
I think the other part of that, Bruce, is even the residue. I agree with Dennis about flux and how many layers access, and the Suleiman pulls water from deep, and its tendency has been to over-predict where you have soils with a high DUL with the way it's kind of stiff configuration. But the residue is going to be another picture to be doing correctly. And maybe some models are not handling that. And when you look at your early soil E, you may want to ask whether the modelers have been able to correctly handle residue issues. Some may not be set up for it.
Yeah, I know we don't do residue at all, and that's a good point. Yeah.
Okay.
I'd be interested in hearing more about how Hydrus works there, Ken, and the Hydrus application works.
I don't know that it has a good residue consideration. That's the problem there. Hydrus probably does mechanistically what Suleiman Ritchie attempts to do with water upflux. But if you know the Suleiman Ritchie, it's hardwired. And those coefficients are, generally based on a regression analysis. And then, what I call the error of the mean doesn't work for all soils, that kind of thing.
Mm-hmm. Okay.
Okay, anything else? Well, I'll be making a much shorter presentation of this whole thing again tomorrow. And I sent out the program for the whole week to all of you, or you probably got it yourselves. I don't know exactly how this distribution works with AgMIP, but anyway, you probably do have the whole schedule for today and the rest of the week. So you may see some of your faces later on. It was good to be able to see some of your faces here. There's a lot of you whose name I now recognize, but I've never seen you. And then I see a lot of names here that I've never seen before that are just listening in today. So thank you for your attention, and maybe or maybe not see you later in the week. Goodbye.
Thank you, Bruce.
Thank you.
Bye, thank you very much.
All right.
Thanks, Bruce. Bye-bye.
Bye. Thank you very much.
Welcome.
Thank you, Bruce.
Thank you so much.